But anyway, let's keep going. So we're going to take a nice leisurely pace with lots of beautiful drawings today. Where did we leave off? We left off, there was lots of drama, and I'm sorry to leave you for 2 days wondering how it was going to be resolved, but we put our object inside the focus of a lens, right? And it just, everything went crazy because the focus was here, right? And the focus was here, and we put the object around the middle like that. And actually, the ray tracing is fine. Remember the 3 easy rays? We've got, let's see, there's always the one that goes forward and through the focal point. Always have that one. There's always the one that goes in between. Always got that one, right? And then the third one is kind of hard to draw, but if you think about it, light going parallel has to go to the focus. So you just pick off the one that would have gone through the object like that. So we drew that. If you can't see that, that reminds me of the other point I forgot to tell you, is that I usually, except for Tuesday, have the notes up before class. So if it helps you to look at those on your computer or print them out, you'll know basically what I'm going to write. I have a PDF of this is usually online. Sometimes I make this 10 minutes before class. Okay, so we had this situation and we say, oh, wait a minute, well, this is bad. These rays are diverging. There must not be an image. What's going on? So what goes on is, if you had your eye here, you would still see something, right? These rays would do something, and your eye would imagine that it saw a ray going like that, and that it saw a ray going like that, and that it saw this ray going like that, right? So there is an image. It's just not a real image, right? It's a virtual image. So we have 2 kinds. We have real images, virtual images. I'm going to give you lots of details about them in a minute, but this was the drawing we were halfway through. And this is the answer. If the rays diverge, then it must be, you can't create an image anywhere, because remember, they have to come together to make it a real image. But you could imagine there was an object back here making these rays, if all this weren't here. See, look at that. Wow, without that there, it looks like it's just an object emitting light. That's how your dumb brain sees it, right there. Let's do it mathematically. 1 over s plus 1 over s prime equals 1 over f. Remember what those are. S is the distance to the lens, between the object and the lens, the object distance. F is the focal length, like that. And S prime is the image distance. Normally, when you have the object in a normal place, you get an image over here, and it's over here. We're going to see what happens when we do something crazy like this. So we're going to put, I didn't say where it is. Is it halfway? Yeah. So let's say here, I meant to draw this. So let's put object inside F, so S equals, and mathematically I'm going to put 3/4 F. Here it looks like I did more like a half, maybe 2/3, okay? But if we do that, we're just going to solve this in terms of F. We're just going to use F and let it cancel. So we're doing everything relative to a distance called F. So you'd say 1 over 3/4 F plus 1 over, where does the image show up? Equals 1 over F. Okay? In a homework problem, you're more likely to put numbers in, but here we're just doing it in terms of F. You could call F 1 meter. Okay? So then we solve for that, and we say, well, 1 over S prime. Get used to turning your fractions around like this and getting common denominators. Right? This is 4 over 3F. So let's make this 3 over 3F. And then that comes there, minus 4 over 3F. So what do you get? You get minus 1 over 3F. Minus 1 over 3F. So you say, where the image ended up, 1 over where the image ended up is minus 1 over 3F, so it must be that the image ends up at minus 3F. Okay? So that is also a property of a virtual image when the image ends up with a negative sign, which means it's on this side. So normally, you've got S is positive this way, and S prime is positive that way. Okay? So the object positive on this, of course, we set that positive. We always start the objects over here, but if the image ends up over here, the last lecture, they all ended up with positive numbers. Now they have negative number. So there it is at negative 3, and that's about right. 3F, it would have been 3F if I really pulled this back. Okay, so it's not to scale here. But anyway, it's negative and it's past F. Right? So that seems to match. And then the magnification formula, it doesn't matter that we put it inside the focal point. The magnification formula is the same. Negative image distance over object distance, right? Equals negative. And then the image distance is negative 3f, right? And the object distance is 3/4 f. So that's equal to 4. All that together. 4? Yes. It was back to school. Never mind. So the 3's cancel, the f's cancel, the minus cancels, and you just have a 4. Now look at this. Does that make sense? Positive magnification means it should be upright. It's upright. Is it 4? Well, it's not quite 4 because I didn't really draw this close enough here. But it's big, right? It's bigger. Okay. It's hard to draw things to exact scale. So that's the answer, is that it made this thing called a virtual image. So let's write a few happy points about virtual images here. Let's see. Things to remember. All right. So one is that they're on the same side as the object. And here I'm talking about just simple situations, an object and a lens. If you get into a complicated 10-lens array, then obviously weird stuff can happen. But in these basic problems we're doing, same side as the object, which means you have a negative value of s, right? Because s is positive to the right. Oh, that's s prime being positive. Yeah, there we go. Right. Right, okay, must be a prime there. Okay. Something was missing, yeah. So you must have a negative s prime, meaning it's on the left side. It's not where rays converge. But where they appear to come from. In case your drawing doesn't make that clear, come from. You'll have it in words. There you go. Straight from the board there. And what are you? They're upright. Meaning they have a positive magnification. Now, could a virtual image ever be inverted? Yes. One way is you could make the object inverted. If I drew the arrow down for the object, then the image would be upside down. Or if you had multiple lenses, you could get a case where a virtual image points down. But I'm just talking about these simple cases. Generally, real images will point down. The way we're setting them up, virtual images will point up. And then finally, since it's not really where rays converge, sort of the famous property is it can't be projected on a screen, right? And when this is something your generation has to understand, that phrase comes from back when there was none of this, and there was none of this. A screen meant a candle, 1850, a candle and a thing, and I can't get it on the piece of paper. Clearly, I could take a virtual image and put it into a camera, and I could project it onto a screen. Okay, that's not what that means. Probably not worth clarifying. Might have changed somebody's life, though. I don't know. We'll see. Okay, so our signs so far, then, are like this. Let's go over our signs real quick. I kind of went out of order and said it already. Signs. So our imaging signs so far. And there'll be more. So we'll say so far are like this, like that. Oh, wait, there's really nothing new here. Yeah, sorry. S is positive. S prime is positive. And remember, for this kind of lens, F is positive. For a converging lens, F is positive. So everything's positive, converging lens. And that's all so we can talk about the next kind of lens, which is the diverging lens. Ooh, yes, I heard somebody getting excited. So that was all converging. So now the second lens type, diverging or convex lens. Okay? So let's think about what it's going to do. Well, let's draw one first. Here we go. It looks kind of like this. Right? Like that. The opposite. Everything about it is the opposite of a converging lens. Optical axis like that. And before we defined a lens by sending parallel rays, and we said, what's it going to do parallel rays? So the other one, focus them to a point. This shape, it's not going to focus them to a point. Let's see. In fact, you could, if you were of a mind, you could do Snell's law, and you could figure out how the curvature affects the angle of all these rays. Right? Because when it's if you're a ray hitting a glass interface and it's pointed like this, that's going to make the ray fall to the normal. Right? So that's what the converging lens looks like. If you're a ray and you see something pointed like this, it's also going to fall to the normal, but the normal's up. So it's going to go up. Okay? Like that. And this one's going to go up, but not as at high an angle, right? Because the curvature's less. The angle is less because it's curved. So it's going to go kind of like that. That one will just go straight. That one will go down, and that one will go down. They'll do something like that. Right? Isn't that pretty? Shouldn't it be concave? Well, of course it should be concave. Yes, you have passed your first test. Concave. It's like a little cave, right? All right. And then the property, though, that we need is that it does that as though the rays are coming from a point. And that's where your focal point is. So rather than focusing them to a point, it diverges them as though they're coming from a point. Parallel rays diverge as though coming from, I would call it the back focus. I mean, the two focal points don't really have names. You could make up two F names and call them that. But basically back meaning it's already past it. So it looks like it's coming from this one, and then they're diverging. Okay? So that's optically what's happening. And you can understand it in terms of Snell's law if you wanted to. Right? So you could draw all the little normals and figure it out that way. Right. Will the light wave refract coming out of the lens? You drew it straight coming out of the lens. Is that the case? Oh, yeah. So that's something about these lenses. They really, of course, refract at both surfaces. Okay? So this is just artistic license. Okay? I'm really just doing them at the front surface. Sometimes I do them in the middle. Sometimes, if I was lazy, I would draw the lens like this. Right? That's this is all, everything we're doing is the thin lens approximation. So the thickness of the lens doesn't really matter. You just say it does that. Yeah. So we could draw it like this. Like that. And this one goes like that. So in books where they're tired of drawing the lens shape, they draw like that. But yeah, you'll see soon. We're going to talk about the thin lens approximation. You'll see why we can get away with that. All right. But yes, very good. They should, of course, refract to both surfaces. Okay, so now we got to figure out how to do our ray tracing with a concave lens. Here we go. Okay, concave, 3 easy rays. Oh, it's very street. Okay, here we go. So let's see. Here is our lens. I'll make it skinnier for you. Shaming my lens over there. And we're going to have an optical axis here like that. Okay. And we need an object. Well, we need focus, right? Focus here, and like that, and an object. All right. We've got to trace the 3 easy rays. All right, here we go. 1, straight. Number 1 is always the one that goes straight at the lens, and then along a line from the focus. Right? Just like we were drawing here, right? Any ray that goes straight looks like it came from the focus, so we just draw this ray. I always like to do the hustle when I draw a ray like that, right? There's easy ray number 1. Let's see, what have I screwed up this time? Let's see. Oh yeah, this is a new one, yeah. Okay, easy ray number 2, through the middle. That's the same. I'll call it the center because I'm being fancy. Through the center. All right, so it's got to go straight through there. And yes, it does refract to both surfaces, but the refractions cancel. And they're hard to see. I drew them there. You just can't see them because it's so small. They're expertly drawn in there. That's number 2. Right? And then number 3 is towards the back F, then straight after the lens. Is it towards or toward? Toward the back F, and then straight from lens. Let's see, is that what I want 2 to be? 3 is well, no, it's toward, I'm sorry, towards, well, I don't know why I called it back. I would call that the front F, yes. Front F, well, the other side. The front is the one it hasn't passed yet in my world. So it's going straight at that, right? Like that. But then instead of continuing on to that one, it does that. Oh, shoot, it does. It goes straight. Right? Because that's what a ray, would do. Right? All right. So that's 3 easy rays right there towards the front. And if you draw those, then normally where the image is very obvious because you just look at where these come together, but it says it's a diverging ray, they don't come together. Right? So we got to think, it must be a virtual image then. Oh, yeah, one of those. So we have to say, what would our stupid brain do that doesn't know this is here? It would say, well, this one crosses about here. Your stupid brain also sometimes curves them, you see. Okay? So you have basically tracing this one back. Well, this one was straight. Tracing this one back, you already drew to draw the ray. You just have to trace the straight one back. And you see there's a virtual image right there. All right? Now let's see real quick. Does it obey the laws or the properties of a virtual image? Good question. Oh, God, this is boring. Is it the same side as the object? Yes. It is where they appear to come from. Is it upright? Yes. Can it be projected on a screen? No. Right? You take these rays, you can't do anything. You can't put them on a screen without a camera. Right? So it really is a virtual image. Take that, Aristotle. Okay. Now we're going to do the math. See, Aristotle had light all mixed up. He didn't understand how it worked. You see. Let's see. Okay, so let's look at diverging lens equations here. All right, what is it going to be? I think my battery's charged now. Let's see. Wait, where is the virtual image? Can you explain why it's there? It's here because this is, remember, virtual image. The rays are never going to cross here. That way, that way, that way. But if your eye were right here, Sauron shit going on here, okay? If you're looking at that and wondering where is it, your eye, you're dumb. Even if you're Sauron, you don't know that there's a lens there. So your eye would say, this ray must go here, this ray must go here, and this ray must go here. And they actually do cross. The virtual rays cross right there. So that's the virtual image. Like, is it from memory? I don't know what that means. Like, is it from memory? Are we talking about Aristotle now? No. Okay, so the equation then. Okay, I can do this. The diverging lens equation. No, I'm going to use this board. I don't care. 1 over S plus 1 over S prime equals 1 over F. It's the same, right? There's no special equation for the diverging lens. Okay, so if we wanted to describe it with a drawing here, we'd say the signs are also the same. This is positive S. This is positive S prime. The object and the image are also defined exactly the same. The one difference is F is negative. Okay, so we'd still draw it like this. But if I said, what is the number you're going to plug into the formula for F, it'd be negative 10 centimeters. You could think of it as the focus on this side is over here and the focus on this side is over here. It's just because it's concave. Okay, so all you have to do mathematically is plug in a negative F. Everything else will work out. Okay, a negative F will give you a negative object distance. Okay, we're going to do it right now just to see. All right? All right, let's see if it matches. Oh, let me erase a little bit. All right. Can you explain the third easy ray? Yeah, we'll end up doing it again because we're going to do so many of these. So we'll do it again. Don't worry. Okay, so let's do it for like what I did here. Let's do this mathematically. All right. Let's do that with the equation. So concave lens, and let's put the object at 2f. So nice and far away. Nobody's getting hurt here. Pretty much what I drew there, I guess I drew it at about 3f there, right? There's f, and then 2 more f's out. I'm only giving 2 f's here for the problem, okay? So let's see. It would be 1 over s, but we're putting in 2f. Okay, concave lens. And now there's one thing we have to do here, is we're going to treat f as a magnitude, okay? Treat f as a magnitude. So we're going to say f is just the number 10 centimeters. And when we plug it in, we'll put negative f for the focal length. Okay. Just because if we want to see the signs show up, we're just going to have to do it this way. So if the number f just means 10 centimeters and we're 2 out, then 20 centimeters. Plus, where does the image show up? Plus 1 over minus 10 centimeters, minus f. Okay. If that bothers you, we could just say it's f, but we'd have to put a negative sign here. Because same thing. Right? We just got to make sure we do the negative sign right. Yeah, we'll get to the third easy ray. Okay, so 1 over s prime. It's this thing you're going to have to get used to doing. Must be 2 over 2f minus 2 over 2f, because now there's a negative sign there, minus 1 over 2f. Ooh, is minus 3 over 2f. So 1 over s prime is minus 3 over 2f, which means that the image shows up at minus 2/3 f. When I flip that back over. Okay. So then we come over here. Ta-da! Right, it showed up at about minus, so it's negative on this side, about 2/3 of f. So it showed up at the right place. What about the magnification? Looks like it should be positive and less than 1, right? Let's see what happens. M, the magnification formula also the same. Minus the image distance over the object distance. All right, minus, what was the image distance? It was 2f. The image distance was minus 2/3 f. What was the object distance? 2f. 2f. And so the magnification is, cancel the f's, cancel the 2's, cancel the negatives, 1/3. All right? Yes, 1/3. Upright. It shrunk it a little bit. What more could you ask for? Right. Let's see. So now we'll do another one. Give us a little more practice with these rays. You want to be able to draw your 3 easy rays for these kinds of lenses here. So let's see. We don't want to use that side. Let's use this. 3 easy rays. Looks like we need to wash these towels. Guess who does that? Correct, I do. Okay. Let's see what the question is. Okay, so now we're going to do it for very far. Why is f negative? Because it's a concave lens. So that's just a property of lenses. If it looks like this, f is positive. If it looks like this, f is negative. The real reason why is because it refracts the rays oppositely. Right? This brings them down. This sends them up. So it's really just based on Snell's law. Okay, let's do object as more practice. Very far from the concave lens. And this will test our drawing abilities here. At least you have like ruled paper. I'm up here without a net, no ruled paper. Of course, I'm not getting a grade, so that matters. Okay, so there we are. Optical axis. Concave lens, focus around here, like that. And I'm going to put this thing way up here. So here's your object, way back here. All right, so 3 easy rays, right? One was straight at the lens and then diverges as though it came from the focus. And I'll do them in the middle, so it won't make you wonder. Well, that's actually worse. It looks like it didn't refract anywhere. There we go. There's one. Number 2, so I'll even number them. There's 1. 2 is probably the hardest to draw because you got to hit that exactly like that. Mine's very curved. Yeah, okay. Whatever. And number 3, so 2 is the one straight through the middle. And 3, oh, thank God that's not my phone. And 3 is the one that is going as though it's going to go through that focus. Okay, this is just embarrassing. Hold on. I just can't go through life with that drawing. There we go. That's quite a bit better. There we go. And that one matters because I got to have the other one on top of it. So now I need one going to there. The middle one, number 2, went to there. I now need one aimed there. Oh, but it doesn't get there. It goes straight. That's number 3. 3, you aim towards the front focus and you go straight. There they are. 3 easy rays. Let's see. Why is it? Yeah. Okay, so now, just like the other one, you don't really need 3 rays to find the virtual image. You really just need 2. Right? We were really done after 1 and 2. It's right there. But if you want to be, this is Rice. You guys want that 3rd ray. I know you do. So there it is. We trace it back, and look at that. It's almost like I planned it. It also crosses right there. So there's your virtual image. Teeny little virtual image. Look at that. Look at that. Right there. Do the numbers real fast. 1 over 10f plus 1 over s prime equals 1 over minus f, because it's converging or diverging lens. So we'll make this 1 over s prime equals minus 1 over f, except we're going to make it 10 over 10f. All right? And then we're going to bring this over and say minus 1 over 10f. All right? That's going to be minus 11f over 10f. So then S prime is going to be minus 10/11 f, which is 0.01010101010101, I think. Yeah. So that would mean it's minus, it's 0.01010111 f. It's on the same side, which, I'm sorry, 0.09090909099999, and therefore it should be almost at the focus. Same side, negative, same side, almost the focus. Voila. And let's look at the magnification. M equals what? The object minus image distance over object distance minus image distance is minus 10/11 f over object distance 10f. Oh, you're starting to see a pattern emerge here. The negatives go away, the 10s, the f's go away. It's 1 over 11. Magnification is positive 1 over 11, which means it's upright. Yes. And it shrunk a lot. Yes. How can this go wrong? It can't go wrong. If your ruler isn't straight, you can screw this up. Other than that, there are ways to screw it up. We'll find them together. Okay, let's stop and take a break. You guys are worn out from drawing these straight lines. So we will stop for 5 minutes and do more exciting cases. All right, let's keep going. I don't have a huge amount left, so I could start talking real slow, or we could actually finish early maybe. Also, I don't like to spend too much time on personal things, but I do want to tell you guys that I've received a pretty major honor. Tomorrow morning at 8 a.m., I'm at my first meeting of the Vision for the Abercrombie Building Committee. I've been chosen to be on this committee by the deans. And when I was a child, I often dreamed of being at a university where the administration had so little respect for my time that they made me be on committees where we express our vision for a new building. So I just want to let you guys know that if you need me at 8 a.m. tomorrow, I'm going to be busy. I can't. I have a lot to say about this. I think it should have walls. I think it should have a ceiling. I think it should be air conditioned. Pretty excited about it. Tell your grandparents, my professor doesn't only teach, he's on a committee about a building. Okay, sorry about that personal moment. I'm sorry. Okay, so now what we're going to do is we're going to do something you've always dreamed of as a child. We're going to put the object inside F for a diverging, diverging lens. You threw me off for a second. This is what you've always wanted. Now, I know what you're thinking, is you like to think, physicists like symmetry. So when we put an object inside a converging lens, it switched from a real image to a virtual image. So maybe when we put an object inside the focus of a diverging lens, maybe it's going to switch from a virtual image to a real image. That's how they like things to work. Let's see what happens. I have built the tension now. Okay, here's the lens. This is our one more practice for the 3 easy rays. We're going to put the object inside the focus of a diverging lens. I'm very excited. Okay, 3 easy rays. Ray number 1 goes straight, and it diverges as though it came from the focus. Okay. Ray number 2. Straight through the middle. Oh, the dream just died. I think that those don't look like they're going to converge to me. Ray number 3 is the hard one. So you thought ray number 3 was hard before. Oh, no, that's not hard. Ray number 3, you draw as though it's going to hit that one. That's what was going to happen, but no, it goes forward like that. All right, so there's 3 easy rays. We usually number them 1. Based on the description I gave that one time, that's 1, 2, and 3. If you're trying to reproduce them later. All right. So, no, sorry, it doesn't make a real image. A diverging lens always makes a virtual image, if it's by itself. I mean, in a train of other lenses, it might do something interesting, but it's always diverging. So let's figure out what would you see if you were looking at it. You'd see where this one crosses that one. So there's your image, your virtual image there. This one, I kind of screwed it here. It's supposed to be up like that. So there, it makes a virtual image right in front of the object. Sorry. Oh, and let's go through the math just because we love to. Let's put the object at 1/2 f, which is pretty much what I drew. I pulled it out a little bit so you could see. Here we go. Last time we're going to do this. S equals 1/2 f. Here we go. 1 over the object distance, 1/2 f, plus 1 over the image distance. That's what we're looking for. Equals 1 over, and I'll put negative f, because it's diverging. Okay, 1 over s prime equals what? We need, well, this is really 2 over f. So it's really, we can just leave this negative 1 over f and then minus 2 over f. Right, I just flip the 1/2 over. And I got minus 3 over f. All right, s prime is minus 3 over f. 1 over s prime is minus 3 over f. Okay, hold on. And therefore, s prime is minus 1/3 f. All right. So someone's asking, how did you know where to draw the image? And that is, so it's hard to see. I know I can't draw this really big enough. But you just for a virtual image, you just trace the rays back. Okay, there's a lot of lines in the way. But you say, my eye sees this ray. My eye is dumb. It thinks the ray keeps going. Right? My eye sees this ray. My eye is dumb. It doesn't know anything's there. This one actually does just keep going because it went through the center. So pretty much where those two cross is where the image forms. I mean, to find the real images is the same thing, right? One just went down, and one went like this, and one went like this, and we said the image is where they cross. Well, it's the same thing. This is where it looks like the images are coming from. This one I screwed up. You're supposed to go straight, and then it's supposed to hit right there if I drew everything perfect. I didn't. Okay? So if you draw this dotted straight back, it should hit that cross, and it would if you did it with like a ruler or something. If you look at my notes, they're all perfect. Okay. But anyway, that's how I draw it, is you trace the rays back, see where they 3 cross, or just 2 cross. Mathematically, you could also do it this way. You get minus 1/3 f. Minus means the image is on this side. Good. 1/3 f, yeah, it's about 1/3 f. There's f. It only went back 1/3 f. And let's finish this thing off with the magnification. Minus s prime over s minus, and here we've already solved everything, s prime minus 1/3 f over, what was the object distance? 1/2 f. Oh, the f's go away, and that is 2/3, positive 2/3. And we rejoice, I think is what I was trying to say. We rejoice that it's positive and 2/3. It looks like 2/3. or there could be weeping and wailing and gnashing of teeth. That's the other one. For every lens diagram, both concave and convex, would our eye be on the right side of the drawing? Okay, so good question. So you only think about your eye for the virtual images. Real images, you just put them on a screen and you look at it and your eye does all the work. But a virtual image, you can't put it on a screen. You could just say there's no image here, right? We could just say this makes an image and this doesn't. But in reality, what you do is when you stick your eye over there, you say, oh, wait, I see stuff over there. So that's why the idea of a virtual image. When we start combining lenses, the idea of a virtual object also becomes important. So that's why this idea is out there. It's where things appear to come from. Yeah, but you don't need your eye for a real image. You just go like this. Oh, I cast it on a screen. Let me go ride my horse back home. I cast it on a screen. Okay, now, somebody in the break, oh my God, asked me the following question. He said, yeah, so why does it have this focus? You know, what is this focus property? What is it? You know, I said, oh, it's just this. It's where this is. But why? Where does this come from? How do you calculate F? So that's what we're going to do next. We're going to get some intuition on where F comes from. All right, so we're going to look at it because it's a little hard to draw. And I'm going to show you the geometry that it takes to make a lens. And you'll have new respect for the lens maker. Okay? But first, let's just start and ask ourselves a little bit about designing a lens and say, what is the lens shape? It's actually fairly interesting. Right? When I bring these big, medieval lenses out here, you can kind of tell they're curved because they're big. But like your lenses on your glasses, it's hard to know what exact shape are they going for. And the way you start is you say, I have an optical axis. You always start with an optical axis. And you say, I have a point source here. This is basically your object, but it's just a point source. We aren't even going to go off axis. All you're going to say is I have a point source, and I want to make a point image here. All right? Now, if you just have rays going off into the wilderness like this, are they going to converge to a point image there? No, they're not. The only way to get them to do it is to put a dielectric interface that changes its shape in here. That's the only way you're going to bend this one and then bend this one more. And then bend this one and bend this one more, and maybe bring things down to a point like that. Right? Except it would be here. There you go. Like that, okay? So the question is, how do you make that happen? Well, so it requires you have to have some change of index, like a piece of glass like that, from 1 to 1.5, and you have to have a curved interface. Right? If we just had a flat piece of glass, what would it do? It would just, even the rays at the angle would just shift angle a little bit, and they would keep diverging out. It requires a curve like this to focus it back down. Okay? So the shape that does this has a name. It's called a Cartesian ovoid. Yes. Some sort of Latin egg shape. It's shaped kind of like an egg, so I didn't draw it well. It should be kind of like, it's not a parabola. It's not a parabola. It's not like a solid parabola. It's somewhere between a parabola and a sphere. It's an ovoid. Okay? But ovoids are really hard to make. Right? It's really easy to make a sphere. When you grind something, you actually kind of naturally grind it into a sphere because as your grinding stone is round and it goes around the surface, it's always in contact at all points. So we can grind spheres. We can't grind Cartesian ovoids in like the 1800s. Okay? So you can't really make an ovoid, but a sphere is another shape that's easier to make. And a sphere does this for paraxial rays. And paraxial rays means small angle and near the optical axis. All right? So what we're saying is, yeah, you need a Cartesian ovoid. But if all your rays are like right here, and you're just staying down here, and you're not going anywhere other than that, a sphere is good enough. Okay? And that's why optics gets to exist, is because we can't, in the history of optics, people weren't grinding Cartesian ovoids. So what we got to do is we have to get an equation that thinks about the radius of the sphere and the index of the material and gets us all the way to the focal length. Okay? That would take a while. I'm going to show you what's involved. This is like now just for fun. This is not on the exam, but I just think it's interesting. So you take a sphere that's index n1, or air is index n1, the sphere is index n2. You draw an optical axis on it. There's where your object is. There's where you want the image to show up. Right? See all that? There's the image. And you say, okay, there's this axis between O and I, and you say, I want a ray to do that, just like we talked about. But I want it to happen on a sphere. So you got to define the height to get two right triangles. You define alpha naught is the angle off the axis, and you define alpha I is the angle inside the glass from the axis. And then you actually treat the refraction case, because you want a normal, so you draw like a line from that's the radius of the circle. That'll hit this point where these two are intersecting, and you now have your normal, right? So now you just apply Snell's law to that. Go ahead and define that internal angle. There's theta incident, right, to the edge of the sphere. Snell's law tells you the angle of refraction is going to be right there, because that's the normal right there. And then you say, okay, well, I have my object distance and I have my image distance. So now I can play with triangles. Here we go. Theta 1 is alpha naught plus psi, obviously. Okay? Theta I minus theta r is alpha naught plus alpha incident. Duh, right? This is all very obvious. And then you basically say this one depends on just the ratio of those two because we're at small angles, right? And then you just mess with that a little bit. And then you say, but it's paraxial optics, so every one of these angles can be replaced with opposite over adjacent. So then you write it like that, where all those h's are over the s naughts and that's over that, and you cancel the h's, and then you get something that looks kind of like that. So you have the index over S naught and SI. So in the end, it depends on the indices, and it depends on the object and the image distance, and it depends on the radius of the glass. Was that a lens? No. We have just successfully put an image inside of a piece of glass. Useless, right? We don't want it inside a piece of glass. We have to keep going. Okay, so that's useless. Refraction at a spherical interface. So now, a lens is two spherical refracting surfaces. Like this. N1, N2, N1, R1, R2. They may have different radii, right? You put the object here, and we want to end up with an image over here, right? S naught and SI, but we've got to call it prime because we're now out of the glass. So you write this for this side, and you say there's that distance, and then you write this for this side, and they're each different. And then you say, oh, but it's not very thick, right? You say the difference between those object distances and those image distances is the thickness of the lens, but you say the thickness is really small. So you set those objects and equals together, and it turns into that when you substitute everything in. Then you add it together with another one from the other side, and you get this. And we get to the one you actually have to know, but we went through the whole thing. That all made sense, right? So we refracted off the front spherical surface. It went down. We refracted off the back spherical surface. So yes, it refracts off both surfaces. And all those equations are how you describe that just as an F. Okay? We could require it if you want. It's really not that. It's geometry, geometrical optics. There we go. But in the end, this is the requirement. Okay, 1 over S naught. This is 1 of the object distance plus 1 over the image distance equals this thing. But 1 over the object distance plus 1 over the image distance also equals what? 1 over F. Right. So this is basically the focal length, or this is 1 over the focal length. So that's the formula that gives you the focal length. So let's write that down and see what we would do with it. See if it tells us anything. Okay? So that's from like the sophomore physics class. And even we don't really care. It's, I mean, we just sort of go through that and we see it and then we say, okay, that's interesting. But what it will tell you some interesting things about these things. So let's go ahead and draw sort of what you would want to know about here. There we go. Okay, so to make a lens, to make a thin lens, based on what we just saw, put two spherical surfaces back to back. And do all that geometry. Okay? So it looks like this. So there's a spherical surface, and there's a spherical surface. Put them back to back. I drew an optical axis, right? And they each have their own radius. They don't, you can have an asymmetric lens. It could have a big curvature here. You could have a weaker curvature there. It could be concave on one side and convex on the other side. Ooh, and you'll be able to use this formula to get the total focal length. So I'm going to call the left side R1. And I'm going to say the right side has curvature R2. All right. And then we're going to say it has an index N2, and we're sitting out here in an index N1. Usually, this is 1 for air, and this is 1.5 for glass. But who knows? We could do something else to make it interesting. So from all that geometry, you get that 1 over F equals N2 minus N1 over N1. It's basically the thing on the right here. Times 1 over R1 minus 1 over R2. Where 1 is what the light is going to see first, if you want everything to work out right. It's going to hit 1, refract, and then refract off 2. This is called the lens maker's equation. Okay? Even lens makers don't care about this, right? They just want this equation so they can make the lens and leave them alone. The lens maker's equation always makes me think of whiskey. I'm not sure why. Something about the name. Okay? Now, or if you promise you're in air, it's a little simpler. It simplifies quite a bit because it's 1 over F. This is 1, right? So N minus 1, and N1 is just 1. So if you're in air, you can just call it N minus 1. And then we're down to just something much quicker and simpler. Okay. But we might do a problem where we say, like, we dropped the lens in water. How did it change? Right? So if you dropped it in water, you went from N1 equals 1 to N1 equals 1.33. All right? Okay. That was exciting. So that's how we calculate properties of lenses. Let's see. But here, let me tell you the trick for doing these problems, and then we'll calculate one lens. Let's see. Okay. This board here. Let's talk about the trick. Hold on, let me get rid of this. There it is again if you didn't catch it. That's great. Oh my God. There we go. Okay. One question. Is R radius? Yes. R is radius. Here we go. Okay, so all we got to do now is talk about the one little sign issue. Okay? Right. So R1 and R2 are, sorry about that, positive if they're convex toward the object. That's how you decide. Okay, there's a negative sign in the equation, but you may have to put positives or negatives in R1 or R2. Okay, it's negative if concave towards the object. So you have to look at it from the object's point of view. Even though here it's a surface going from glass to air, it's concave, right? Convex, concave. So you have to decide what to plug in. So let's look real quick. Here's a lens. Right, this side, R2 is 10 centimeter radius of curvature. R1 is 10 centimeter radius of curvature. So it's a nice symmetric lens, same on both sides. The index is 1.5, and we're using it in air. All right, well then, let's see. What is 1 over F? N minus 1. Boom, 0.5. So if you're doing this in air with glass, this pretty quickly becomes a half. Right? 1.5 minus 1 is 0.5 over 1 is still 0.5. Okay. And then here, now we just follow the formula and follow the rule. 1 over R1. And R1 is convex, because it's sticking out. 1 over 10 centimeters. Minus 1 over what? Is that convex or concave? It's concave. right? It's a convex lens. It's going to focus light. It's converging, blah, blah, blah. But if I am just a light ray coming this way, I see this as concave. So I put negative 10 centimeters down here. That's why the negative is there. So those two negatives can cancel. Okay. And when you do that, this becomes what? 1 over 10 plus 1 over 10 is 2 over 10. So it's 1/2 times 2 over 10, and it's equal to 1 over 10 centimeters. The focal length is 10 centimeters. So if you have a nice symmetric lens with the same radius on either side, you'll get the focus is just the radius. But that's because the index of glass happens to be 1.5. Right? If you had a different number here, you wouldn't have exactly a half right there. That's just sort of one of those things that the universe happens to be this way, therefore we exist. The universe happens to be that way, therefore R equals F, the heuristic principle in action. I think that's what it's called. I don't know. People somehow can get funding to sit around and think about that. I don't know how they do that. Okay, so let's calculate one more lens. And then I'll think of another personal story, or we can leave. I don't know. We can decide. Or I'll sit here and answer homework questions. Ugh. Let's calculate a diverging lens with this new found ability that you have here. But let's make it interesting. What do you say we make it interesting? So here you've got 10 centimeters there, right? And a steeper radius there. R1 is 10 centimeters. R2 is, put 30 centimeters, right, for diverging. So 1 over F, let's calculate it. It'll be one of those that you'll get used to, and you won't even have to use the equation. You'll be like, well, yeah, 1 over S prime plus 1 over S equals 1 over F. Here, 1 over F, okay, 1.5 minus 1 over 1. Wrote it out for you there. 1 over. Now, does this thing look convex or concave? It looks concave. So I'm going to put a negative sign on this 10 centimeters. All right, and then minus. And now, is this convex or concave? Well, it's really concave when I feel it with my hand, but you don't do this by feeling it with your hand. You do it by your light ray coming along, so it looks convex. So I'm going to leave it positive. Maybe you're getting a feel for how it works, right? That's why that negative sign is there. That negative sign is there because the concavity, the constantinuity switches when you go the other direction. That is a word. Look it up. Constantinuity is a real word. 3 over 30, 4 over 30, 30 over 4. 4 over 30 negative, and I got negative 15 centimeters. I got, it's 1 over that. So I get F equals negative 15 centimeters. So sure enough, a lens that is concave on both sides to your hand is going to be a diverging lens. And the focal length is in between the two. Because of glass, you could actually just average them, and you'll get the focal length. What if we dropped it into water? I'm going to put that on the homework for sure. Would it get longer or shorter? Let's see. This number would get a lot smaller. So the 1 over F would get smaller, so the F would have to get longer. Right? So that would happen if you change the index around the lens. I don't have any more. Oh, I guess we have to stop early. I apologize. You're not getting your money's worth today. I didn't know I could draw that fast.